Greetings pre-calc students and anyone else out in TV land watching this video. Mrs. D here to do some demonstrating on how to solve some real life situations that would involve rational equations. For our first problem, we're going to look at concentration of different solutions. Two solutions combined to make a new solution with a desired concentration. This is found in your pretty pink packet, problem number 15, where we have 50 ounces of a 15% saline solution. We are adding, we don't know how much, some unknown amount of water to dilute this solution so that the end result is 10% salt. Now the concentration is calculated in a rather simple way. Concentration of any substance is found by taking the pure amount of substance compared to the total amount of the mixture. And so our 15% saline solution must have had 7.5 ounces of pure salt. That could be calculated by multiplying 50 ounces by 15%. You will see that 7.5 ounces of the 50 ounces must be pure salt. Now when we add water, we're not adding any new salt to the mixture. Notice if you count all my little spots here, we probably still have the same amount of salt, but with more water in it, it's diluted. So 7.5 will remain ounces of salt, and our total mixture now is X plus 50 ounces. The desired concentration is 10%, so when we divide, just like having a quiz score or a test score, the number right divided by the total, that always gives you a decimal form of the percent. 0.10 will represent 10%. This is a rational equation. To solve, I'm going to multiply to undo the division. I will multiply by x plus 50 on both sides. That will get rid of this denominator, leaving me with a nice linear equation. 7.5 equals 0.10x plus 5. To solve, I will isolate x to one side of the equation, the constants to the other side. 2.5 then is 10% of some unknown amount. Divide by the 10%. And we have x, which is the amount of water to be added, is 25 ounces. We will check this answer. If we add 25 ounces of water to 50 ounces of 15% saline solution, our mixture now has 75 ounces. Wow, that's really hard to read. And remember, we have 7.5 ounces of pure salt. So 7.5 out of 75 is exactly 10%. Correct, we have achieved 10% saline solution. Here's another problem dealing with percents. This problem is about a gal named Bethany. She is shooting free throws, and right away I'm curious about how she's doing. We have 10 free throws made out of 18. Her percentage thus far is 55.5%. She would like to do better. So if she continues shooting her free throws, we would like to bring the average up to 68%. Remember, the percentage can be calculated by the amount, in this case, of successful free throws divided by the total amount of her attempts. Now, Bethany is not allowed to miss any more free throws. That's why we're trying to see how many consecutive free throws she will need to make. That will be x, our unknown, the number of consecutive makes. Oh, she made it. Okay, how many will she need to make? Well, she's only made 10 so far. We will add to that however many she makes. Likewise, the total attempts will have increased by x amount as well. So now she has 18 plus x total shots Our goal is for that to become 68% success rate. So the decimal equivalent to 68% is 0.68. Here's our rational equation. So if we multiply both sides, of course I could try to get a common denominator on both sides, but I think this is the most efficient solving method. If I multiply both sides, that will undo the division, leaving me with 10 plus x equals 12.24 plus 0.68x. And if I get x to one side of the equation and my constants to the other side of the equation, I will be left with 0.32x equals 2.24. Final step of division, if you divide by 0.32, we find that x equals 7. 7 more free throws that she will need to make in order to increase her average to 68%. If you want to check that real quick, she will have made 17 free throws now out of 25 total attempts. Is that 68%? Yes, indeed. Our third and final example with rational equations is in a different category. This would be what I would call distance or rate applications. Here we have a steamboat that can travel a certain speed. Speed itself is a rate. We are comparing miles to hours here. We could be comparing cookies to people. We could be comparing inches to seconds. Lots of different rates, comparing two different quantities. So this steamboat can travel at that speed, 15 miles per hour, if it's in calm water. But if you continue reading this problem, also found in your pretty pink packet, problem number 10, you will realize this boat is not in calm water, it's on a river. Rivers have current. So the speed of the boat, its maximum speed, let's say, that's its ability is to go 15 miles per hour. It will be affected by the current. So let's say when we're going upstream, that 15 miles per hour speed is slowed down by the current. However fast the current is moving, it slows down the boat. And when we're traveling downstream, that 15 miles per hour potential is increased, thank you to the current, at whatever rate it's moving at. Now at this point you might feel like you don't know how to write an equation. We do know that it's 20 miles traveled up the stream. It's also 20 miles traveling back down, and we have a total of 4 hours. This is the time where I feel like we need to look at the relationship between these quantities. So distance, speed, and time are related in many ways. Often for people, the speed measurement is simply calculated by comparing distance and time through the operation of division. Distance divided by time, just like miles per hour. It sounds pretty simple. Distance, if you've taken any physics classes, is calculated again with the other two quantities, speed and time. If I'm driving a school bus, for example, at 60 miles per hour for 3 hours, hopefully it's common sense that the total distance traveled would be 180 miles. That quantity is found by multiplying speed times time. Now these two relationships are used often. The third, the value of time, is not often thought of, but if we rearrange either one of these equations and solve for time, you'll find that time is distance compared to speed, distance divided by speed, that is. And this is the relationship that we're going to need to use in order to solve this steamboat problem. And so upstream, the distance traveled is 20 miles. The speed, remember, is 15 minus c. It's slowed down by the current. Downstream, we are also traveling 20 miles in this steamboat. The speed is increased by the current. And these two expressions show us the time spent traveling upstream and the time spent traveling downstream. We know that the total time for this trip, two-way trip, is 4 hours, and that's found by adding the two times. Totals are often found by calculating a sum, and there is your rational equation. To be solved by finding a common denominator, let's say, of 225 minus c squared, which can easily be acquired by multiplying the two fractions by, the two denominators by each other. So this first fraction becomes this, and the second fraction, when we multiply by the other denominator, becomes 20 times 15 minus c. The common denominator simplifies the problem so that you can actually add the fractions. Notice when you distribute here, you're going to get 320c. You're going to get 300 and negative 20c. Those two c terms will cancel out, leaving you with a nice 600. Now again, even though we acquired the common denominator, I don't think we need to do that on both sides of the equation. We can now multiply by the divided amount, which is 225 minus c squared. If we do that on both sides, we will be that much closer to finding c. So 600 will equal, if I distribute, 900 minus 4c squared. If I continue isolating by moving quantities from one side of the equation to the other, or removing, I should say, we will find that c squared is 75, which means c is the square root of 75. You tell any steamboat captain that's how fast the current's moving, and they might not understand it, so let's give a decimal approximation. The river's current is approximately 8.66 miles per hour. Confirm these results if you would like. Check the speed of the steamboat with the current going down the stream. Check the speed with the current going up the stream. And the total time should be 4 hours. Happy solving. Continue trying every problem. Set up, solve. If something doesn't seem right, don't be afraid to go back and reconsider the setup of your equation. Mrs. D signing out.